So can we start the meeting? Let us start. Give me 1 minute. Let me join my. So today we will discuss last assignment. Let me share slides. Okay, so let's start the meeting. First, let's understand the structure factor. And so phase difference between two is, let's see, there is a crystal diffraction from a crystal. You can see there are crystal atoms, and wave incident. This is, let's say, normal reflected. Okay, similarly from here, so on and so forth. So phase difference between the wave scattered by atom at a position B. You can see here is B. Let me different color. B, and scattered by a atom at position at a here. Okay, for the HKL reflection, we know fast phase difference phi equal to 2 pi h u, if the u, v, and w the position are the coordinates, and so h u k v l w. Okay, so this is the length here x, and this is the total lattice side, let's say a. So scattering any wave is expressed like that: a e to the power phi exponentially iota phi. So here we consider f. This is the atomic structure factor, e to the power 2 pi I. This is the phi. If a unit cell consists n atom, then we can write, so this is for an atom 1 to n, the structure factor Fn e to the power 2 pi I hun n equal to 1 to n capital N. So this is the structure factor. Okay. So please remember this formula, structure factor. Now intensity, we know the intensity is square directly proportional to the square of the amplitude. So let me take different color. Intensity है directly proportional to the structure factor, also the multiplicity, also the Lorentz polarization factor, and also temperature factor and absorption also. Intensity depends these parameters. It is doesn't include effect of the that can sometime can problematic, such as a preferred orientation and extension. Okay, but these parameters are included: multiplicity, absorption, temperature, and Lorentz polarization factor. Let's see multiplicity. Do you know what is the multiplicity? So let's say consider 100. So multiplicity of this plane, family of plane, we can see, we can arrange first, second, third, like that, also minus. These are equivalent. So multiply factor are 6. Okay, similarly 110, this is 12. So you can see 4, 11, 110, 211, these are the multiplicity. Or for this, the multiplicity are lower in lower symmetric system. For example, in tetragonal crystal, equivalent to, but not these and these. So intensity of the powder pattern lines. This is not including the temperature and absorption factor. Only structure factor, multiplicity, and polarization factor. Okay, so we can calculate, apply this formula, including the multiplicity and polarization factors. Let's discuss first question. The first three peaks in XRD pattern of BCC structure material are. Please calculate and choose the correct options. We have already discussed. This is body centered cubic structure factor, one at body, either let's say so position for this 0 0 0, and for this half half half. Okay, so structure factor, please calculate summation of I 1 to n equal to head 2 phi to the power 2 pi iota this is the formula. Three peaks. So how you choose which peaks are available or which peaks are not available? So if peak are available, then this structure factor will be not 0, otherwise 0. So put these two atoms in this equation. Let's say F common 0, all are 0, and other 2 pi and half. This is H K N. If H plus K plus L are even, HK plus R if odd, what will happen? E to the power 2 pi to the power pi. You know e to the power iota theta equal to cos plus iota sin theta. If this is the case, cos pi plus iota sin pi will be 0, this is 0, 2 pi will be 1. So this is odd, then minus 1 will be 0. If the will be 0 not equal to 0, 2f, this is equal to 2f, even if 2f. So HKL we have to choose such as that line should be even. So we can say 1 1 1 0. These are the planes. If we put and consider BCC for BCC only even numbers, some gave even, this is 3, this is not, this is also not 2, this is also not, but this is the correct answer. So you can find like that. Okay, if HKL are given, then first you find the structure factor, then find the condition and put these planes, then you will get the right answer. Okay, so these are the condition. This is come from structure factor F. So structure factor you already know how we can calculate. UVW HKL Okay, so apply this formula, you will get these conditions. So I think clear to you. Now second question. Following is are not correct statement about X-ray diffraction from crystal. Not correct statement about X-ray diffraction from crystal. Intensity of the peak is proportional to the half of the square of the structure factor. Half. So this is not correct. The structure will depend on the unit cell shape and size. Structure will depend on position of the atom and unit cell. Structure factor depend on the element in the crystal. So these are the options. Intensity. This is not correct statements. Okay, choose correct, not correct statement. So these are the false statement about the XRD, X-ray diffraction. Structure factor depend on the unit cell shape and size. This is also not right option. Okay, this is correct for the XRD. Depend on the position of the atom in the unit cell. Structure will depend on the element in the crystal also. How? We have already seen first slides. Let's see. You can see the atom position in the crystal and element, how many elements are present. So intensity directly square proportional to, and we can see also small f. This is included atomic structure factor, which is we can see atomic structure factor is given by amplitude of the wave scattered by the atom and amplitude of the wave scattered by the one electron. Okay, we can consider an atom to be collection of electron. The electron around an atom is scattered radiation in the manner described by the Thomson. However, due to the coherence of the radiation, we need to consider interference effect from the different electron within an atom. This leads to strong angular dependency of the scattering. A quantity F, atomic scattering factor, is used to describe the efficiency of the scattering of a given atom in the given direction is ratio of amplitude. This for any atom scattering in the forward direction, F is equal to the its atomic number Z in forward direction. As theta increase, the wave scattering by individual electron become more and more out of phase and F decreases if theta increases. The atomic scattering factor also depends on the wavelength of the incident beam. At fixed value of theta, F will be similar with the shorter wavelength since the path difference will be larger relative to the wavelength, leading a greater interference between the scattering beams. The actual calculation of F involves sin theta rather than theta, so that the net effect is F decreases as the quantity sin theta by theta lambda increases. The scattering factor is sometimes called form factor because it depends on the way in which electrons are distributed around the nucleus. So this is all about by atomic scattering factor. So it is X-ray. We can see structure factor is dependent on the element in the crystal and position of atom in unit cell, not depend on shape and size. So let's discuss next question. In a powder diffraction experiment using copper K alpha radiation wavelength in nanometer 0.154 nanometer, the first 5 peaks are observed from a monoatomic cubic crystal. When the angle to theta are given this degrees, what will be the structural material? Simple cubic, body centered cubic, face centered cubic, diamond cubic. Please calculate. You can take 5 minutes for this question. So these are theta are given. Sorry, two theta are given. So let me find theta. Then sine square theta. Then sine square theta by sine square theta minimum. So let's find the theta. Two theta are given. 38, 54.2, 64.4, 77.2, 51.4. Last one, 81.4. This is 40.7. Now calculate sine theta, then square. This will be 0.425. Then 0.599, 22, then square. Thirty-two, 39. So this is sine square theta. Then sine square theta by sine square minimum. So this is minimum. Consider this is minimum, and divide by 5. So this will be, I think, something is wrong. Okay, let me check. Check to checking sign, checking sign. Okay, so this is wrong number. This would be 0.415. So this will be 1.33 and 0.389 divided by 0.005. This is 7.425 divided by 4. So this is around 4. So multiply by, let's say, 2, 3. Sin square theta divided by sin square theta minimum, multiply by 3, let's say 2, 3, 4, 1, 2. We have to multiply minimum number 1, 2, 3, 4, 5. So multiply by 2, then what will happen? We have to make a perfect integer. So when we multiply 2, this is not 3, then 3, 1.33 multiplied by 3. This is approximate, then 3.67. And multiply. So perfect 3, this is 4, this is 8, this is 11, this is 12. This is equal to HKL square. Then HKL, what is HKL? 111 200 220. So these are the planes, and this is corresponding to, if HKL square 3, 4, 8, 11, 12, this will be FCC, has centered KV, or HKL unmixed. You can see if FCC, HKL must be unmixed. All are even, all are odd. So you can see HKL, these HKL unmixed. Okay, so you can find like that the answer. Next question: which of the following characteristic of material can be accurately determined by X-ray diffraction technique? Which of the following characteristics of material can be accurately determined by the XRD? So option is B and C are correct. Identification of phase in the material or determination of strain in the crystal. So application of XRD: phase identification first, determine crystal size, strain, of lattice, advanced version of XRD, crystal quality, texture, atomic position. We can also find. These are the application of XRD. Okay. Next question. Which of the following is the diffraction condition for the abscissa lattice? How one can find? Please find this condition for abscissa. So we know abscissa lattice. Let's say these are the atoms and position these atoms 0 0 0 first, then half, half 0 0 half half and half 0 half. These are the position. Then find the structure factor. Let's say f to the power 0 first for this. That's a common f. If the atoms are same, 2 pi and half 2 pi and okay. So if this is 1, if this is HK, K, L. Now, so answer B is HKL are mixed. How? If let's say HKR all are even or HKL are odd. That first case. For even let's say 1 1 sorry 2 0 0 let's say sum of two evens also even. So these are, if this is even, then 1, this is 1, this is 1, this is f equal to 4f. If r odd, then odd by r 1 minus 1 minus 1. Sorry, something is minus 1 means FCC and then HKLR must unmixed. give events. Okay, we do what it is. HKL of then F to the power. This is 1. This is H plus K plus 7, H plus 7. So even if H, K, L are evens, so then what happen? This is F equal to even, this is also even if odd H, K, L. So let's say number odd means let's say 3, 1, 1. So what happened here? This is also 3, 1 equal to 4. So this is 1, this is also 1, 1, 1, 1. This is also 4. So even in odd case, if unmixed, then this is factor will equal to 4f. If mixed, then f will be 0. You can check even or add if these are mixed. Okay, so next, in a powder diffraction experiment, copper K alpha radiation of Babylon, this copper for copper 0.179 nanometer. What is the diffraction angle for the first order 220 set of planes from the FCC crystal iron with lattice parameter? So we know 2d sin theta equal to n lambda, n equal to 1, lambda equal to 179, and we have to find theta, and what is d? D equal to 4 FCC. So A is already given 2866 nanometer. HKLR also given 220440. So you can find here D. Okay, now apply this equation 2D 222 sin theta equal to n lambda. We have to find theta n equal to 1 and lambda 179. Okay, multiply by 2 divided by 2866 in nanometers. Nanometer cancel out. So what is this value? Point 0.9 divided by 2.66 meter. 0.8831 approximate. So theta will be sine inverse of 0.8831. So theta will be approximate. Option A is correct. Okay, you can find the theta like that. Next question. Which of the following is are zero dimension defects? So let's discuss about defects. So zero dimension defects, so defects interstitial or missing, oh, you can see in slides, missing atoms, interstitial atoms, substitutions atoms, Franken or Schottky defects. These are the zero D or points defects. Next, which of the following is are referred to equilibrium thermodynamic defects? Dislocation, grain boundaries, vacancies, Schottky defects. Equilibrium thermodynamics defects. So answer, we know C and D. Why? These are zero D defects, so these are the equilibrium thermodynamics defects. Next, find the equilibrium vacancy in 1 centimeter cube copper at 1000 degrees Celsius. These are the given. Activation energy, let's see Q. So apply this formula. Please find the, this is a related activation energy. Equilibrium vacancies, please find. You can take 10 minutes for this question. Please find the answer. So please apply this formula. Please find out the vacancies in this question. Let me simplify more. For this n, you can apply density, Avogadro number, and atomic weight of Cu. So ASU is given this 63.5 gram per mole. Density is given 8.4 gram per centimeter cube. Okay, density is given. We know Na equal to how much? 6.02 into 10 to the power 23 upon density of, this is density molecular weight 63 gram per mole. This is for 1 meter cube. So convert please in meter cube and please find this number. Then apply this formula and K, you know K 8.2, sorry, 8.62 10 to the power minus 5 electron volt atom per Kelvin, and T also is given 800,000. So this is will be in Kelvin. Please put these number in this equation. Please find small n. Okay, you can take 5 to 10 minutes for this question. Please solve. Please tell me this number and also this number. Yes, yes, Hejal. Please ask if you have doubt. You can write in chat box also. Please solve. I am waiting. So this is approximate. Please calculate. Are you getting this number? Yes or no? So let me solve. For small n and multiply exponential minus q, let's qd activation energy upon kt. So n 2428 exponential q is given atomic 0.9. This is minus 10 electron volt per atom, and cavity is k 8.62 10 power minus 5 ev by atom per Kelvin into multiply Kelvin. What is Kelvin? 1273 Kelvin. Please find out this number. Simplify. N will be 2.7 10 to the power 2. This number will be this, and this 8.2 10 to the power 25 vacancies. So if you have any doubt, you can ask. Clear to you? Let's move for next question. Shortcut defects is for pair of anion cation, ion vacancy or ion interstitial, pair of cation vacancy or anion interstitial, pair of anion and cation interstitial, pair of anion and cation vacancies. Which option is correct? About Schottky defects. So pair of anion and cation vacancies you can see in slides. Vacancy, interstice substitution and pair of defects, ionic solids, Frankel or Schottky defects. So this is related to the anion and cation vacancy. Next question. The theoretical ratio of the intensity of the first two peak in the XRD pattern BCC material is. Also, please calculate for FCC and BCC. You can take 10 minutes for this question. Then I will discuss. So theoretical ratio of the intensity first two peaks in XRD pattern BCC FCC material. So we know intensity is directly proportional to the amplitude square. Okay, or we can say I1 upon I2. So first d square interplanary. So I1 upon I2 we have to find T1 upon T2 whole square. Okay, so you have to find this. For this, let's see. For 110 then 200, you can see we have to 200 divided by 110 d spacing square d we can find 200 and similarly 110. So 110 h square hkl square this. So after squaring we will get this 14. So okay, this will be half. Similarly, you can find the planes, then calculate the intensity. Okay, this is the methods for BCC and FCC. So this is for BCC 24 HKL. If HKL is for 2486 like that, then BCC. FCC 34 dot 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 HKL square. So BCC, similarly you can also calculate for BCC, FCC, sorry, 110, sorry, 111 and 200 for FCC. Okay, next question. The vector of dislocation in case of BCC lattice is, so answer is B. You can see Vector vector for FCC along the 110 direction, 110 a by 2. So amplitude for FCC a by root 2. But in the case of BCC along the 111 plane direction, sorry, along the direction 111 and by 2 a by 2 lattice pattern. Then if we calculate the magnitude a by 2 multiply root 3. So this is energy related to the budget half GB square. This is shear medulla and this preserved budget vector. Okay. Next question. If the element having BCC crystal structure has lattice parameter 3.57 angstrom, what is the magnitude of the budget vector? BCC. BCC along the 111 direction. 111 direction. So please find out the magnitude of this vector. You can take 5 minutes for this question. What will be the magnitude? Then put the number. A is given in angstrom. We have to also calculate in angstrom. Please calculate this number. Three. This will be around 3.09 10 to the power minus 10 BCC. So that 3.09. Okay. So clear to you? Let's move further. This is the formula. Yes. The copper share modules and lattice parameter are given. This is 20 gigapascal and lattice parameter. What is the elastic energy? You have to find E. Apply this formula. Please calculate the numbers or elastic energy. You can take 10 minutes for this question. Copper has FCC like structure. So B, you can see FCC A by root 2. Please calculate. Yes, please calculate. One giga equal to 10 to the power 9. Are you clear this question? So something else. Yes. B option is correct. Let me some correction is there. Let me correct out. Okay. So B is correct answer. Next question. The structure factor order CSCL will be. Please find out this question. Correct option. You can take 10 minutes for this question. One atom at center. Let's say this is Cl, Cs. This location half, and let's say for Cs 0, 0, 0. Now please calculate. So we know the structure factors summation of atoms 1 to n. So 1 to n equal to this is different. This is okay. So there are two atoms. Let first Cs 0, then Cl to the power of. So this is the structure factor for CSCl. Now, if H, K, N are given, even then this is will be S plus Cl. Even if odd, then this will be minus Cs minus Cl. So which option is correct? Even case is plus, odd case is minus. C. Next question. The NaCl has a cubic lattice with 4 Na and 4 Cl atom per unit located at 0, 0. This is Na location, this Cl. Find out the structure factor. You can take for this question 10 minutes. Then I will discuss. So let me discuss the solution. Na has a equal to 0 0 of this is for Na, and so we put plus Cl okay. This will be pi plus, this is okay. Now simplify this question. Let let take the common e to the power of pi plus k plus n. This will be 1 pi h. Okay, understood. And we know to the power, yes or no, exponential to power minus n pi equal to pi. Let's say n multiply by n. We know apply here, then what will you get? So we can take common this and okay. So if we take HKL mixed, then F will be 0. If H plus K plus L even, then we will get, if we get even, then we will get this number. Please apply. And if we get odd, summation of odd, then we will get minus. And this number Q is 4. Okay, so this is the way you can solve. Let's discuss something is more about microstrand and XRD. You can say intensity should be like delta function, but there is instrument error, crystallization sizes, and lattice strength. So microstrand and ideal strand free crystallized D spacing are uniform through the X-ray by atom plane interfere constructively at a specific well-defined angle leading to sharp diffraction peak. But microstrand in the crystal lattice microstrand refer to a small non-uniform deformation or distortion within the crystal lattice due to the dislocation defects, residual stress, or external forces. And when microstrand is present, the lattice spacing is not consistent across the entire material. Instead, they vary slightly from one region to another. And this is the formula. This is related to the crystal die size. This is microstrand eta. Beta total is FWHM. We can see here WHM peak broadening at, this is FWHM at half intensity maximum, half of the intensity maximum, full width half maximum. Theta is prime angle. V, K is shape factor, typically is 0.09. Spherical grain. Lambda is X-ray wavelength. D is average crystalline size. Epsilon is microstrand. Crystalline size effects we can see. Consequence of the reduced number of planes available for the coherent scattering in the similar crystal slides. Fewer repeating planes which limit the distance over which the wavefront can constitute interference. Fewer repeating planes limit the distance over which the waves interfere. And from the slope here we can calculate the microstrain. The slope of the derivation is microstrain and y-intercept we can be crystallized size. So this is all about today lecture. If you have any doubt you can ask. So this is the last assignment. If you have any query you can ask. Today we have discussed how we can structure factor form, which is dependent atomic arrangement, number of electrons present in the, and also intensity, structure factor, multiplicity, Lorentz factor, temperature and absorption. So this is the way we can calculate the multiplicity, and this is the formula of intensity, which is included structure factor, multiplicity and and polarization factor. BCC crystal we have discussed. So these are the condition for simple cubic or HKL are permitted, but BCC H plus K plus L are even should be or odd. If odd, there is no diffraction. If is even, there is diffraction. So these conditions come from structure factor. Then similar question about the intensity peaks, also the structure factor. This is atomic structure factor. Then question about 2 theta. Then we can calculate the type of simple cubic body center of abscissa. Then we have discussed about the utility of the XRD. We can calculate the phase identification, determination of crystal size and strength, advance in XRD crystal quality, texture and atomic position. Then here we calculate the structure factor for FCC, and condition is HKL must be unmixed if XRD is present, diffraction is present. Then theta here is calculated for FCC structure. Then discussion is about zero D effects. Also zero D effects, equilibrium thermodynamics effects. Then number of vacancies we have calculated for given copper. Shortcut effect is pair of anion and cation vacancies. Then theoretical ratio of intensity we have calculated. Then Virchow vector, magnitudes and elastic energy. Then CSCL is crystal structure for CSCL, and next for NSCL. Then We can also study the microstrand related in XRD WH plots. Okay, so this is all about. If you have any query, you can ask. This is the last class of your course. So, best of luck for your exam and thanks for your interactive sessions, your participants, and during the lecture discussing the question answer. Thanks to all of you. And best of luck for your exam. If you have any query, any doubt, you can email me. My email ID is given in slides. So let's stop the class and thanks again, all of you.